Quantum factoring algorithm was the first algorithm where computer scientists started perhaps taking quantum computations more seriously. You see, until Peter Shor and until this factoring algorithm, all examples that I described to you, that was Deutsch's problem, Bernstein-Vazirani problem, Simon's problem, all those examples were based on black boxes. So we had oracles, and we never bothered to ask the question, how difficult it is to compute such a function. So the complexity of the quantum function evaluation was not really the issue, because it was just one computational step. Now with Shor's algorithm, we are talking about real computation. We are talking about building polynomial size uniform family of circuits, which does the job, does the factoring for us. And then we can start really comparing seriously the power of classical and quantum computation. So we can draw complexity classes. That's what computer scientists love to do. So they want to see what kind of problems you can solve efficiently using classical computer, using a randomized computation, using quantum computation. And usually we start with a class P. Remember, that's a class of problems that a good, proper, classical deterministic computer can solve in polynomial time. And now we add randomness to the whole thing, and when you add randomness, you have another class. If you allow your computer to toss an unbiased coin and view it as a resource for computation, that it's possible, it's not clear, but it's possible that with this additional resource you can efficiently solve problems which are not in P. In fact, so we call this class BPP. It's bounded error probabilistic polynomial time. And bounded error comes from the fact that we expect our randomized algorithm to come with the answer yes or no. Most of problems that we look at in the whole field of computational complexity are the so-called decision problems. So you can reduce all the problems to simple problems or simpler problems where the answer is yes or no. It's kind of a decision problem. So if you look at the decision problem in this particular class, you would like the probability that the answer is correct to be say half plus epsilon, where this epsilon is fixed. It doesn't depend on the size of the input, and therefore when you run your computation several times and take, say, majority voting, then you can then show that the probability of error in the majority voting will go exponentially to 0. There is something called Chernoff bound that you can use in this case, and you can show that the probability that things that you will get it wrong by following the majority voting will be just e2 minus something of the order of r. R is a number of repetition, and say epsilon square here. But we want to have this epsilon bounded in a sense. We don't want this to, for example, come too close to depend on the size of the input and perhaps come very, very close to half. For this, there's another computational complexity class, but we will not talk about it. So that's bounded error probabilistic polynomial time. There is a big debate in the computer science community where this class is really different from P. Most computer scientists believe today that if you find a efficient algorithm for a problem here, most likely it will be reduced to the problem in P, so you can randomize it. And then the class that we are really interested in, we add additional resource. We go from deterministic to probabilistic, and now we go to quantum. And then there's a larger class here that is BQR. p. So it's a bounded arrow quantum polynomial time. And this is the class we are really interested in. We would like to populate this class with all kind of problems, and we would like them to be here. So factoring is one example. So we would like to find problems which are in BQP but not known to be in BPP. So factoring was the first example where we could see this separation. And then, of course, you know, this BQP is in a larger class, and I can draw the whole, you know, a set of diagrams here. It will get more and more complicated, but so let me just draw maybe two more. So a larger class here is something that you call P space. So that's about the polynomial use of memory in the process of computation, a class of problems that you can solve with a polynomial use of memory. So BQP is known to be in P space. And the reason for that is, remember, when we started talking about quantum theory and how we make predictions, how it is a new kind of probability theory, I told you that it just boils down essentially to multiplying probability amplitude, then adding them together, and then taking mod square. So, of course, you know, if you take a classical computer and want to do all the calculations, then if you have, for example, n qubits, then you will be dealing with 2 to the n exponential number of probability amplitudes that you have to add together. So that may take lots of time, right? But it doesn't require so much space, simply because you can do addition, you can keep the running sum in your register, so you don't have to keep all those 2 to the n different terms in your memory. You just simply start adding, and you keep on adding and keep the sum in the register. So you just simply keep the running sum in the register. For this you need only a polynomial space. So quantum mechanical predictions can be sorted out on a classical computer, and it may take exponential time, but the use of space, use of memory, is at most polynomial. And then, of course, if you go outside P space, you have this class of problems that require exponential time, exponential use of memory, exponential everything. They are really tough. So you see, the thing here is that we are not claiming that all problems that are all difficult problems will ever be solved by a quantum computer. We would like to stretch this border as much as we can, and I'm not going to draw a few other complexity classes, but we would like to populate this BQP as much as we can. So I think, you know, we want to see many good problems in this class, and that's what we would like to do. Now, there are problems where you don't have exponential separations like the factoring. There are problems that we know that we cannot speed up using quantum computation. So they're usually problems where you have to look at some unstructured database, and then, you know, there are some speed ups, but they are not as conspicuous. They're not exponential. They could be at most quadratic, and they are related to the fact that when we calculate probabilities in quantum theory, we take mod square. So the quadratic speed ups are kind of expected, but the exponential require that you use the structure of the problem. There is something there that lends itself to quantum speed up. What exactly it is, well, we don't quite know, but one thing that should be obvious to you, when we look at all kind of problems that you could see the speed up, they were related to some global features of functions like periodicity. So in Shor's algorithm, you can actually get the period of the function, which is a global property of the function, without knowing all the values of the function. So in quantum theory, it's possible to measure a certain global property without knowing all the values of the function, so which is cool, right? And that's why we have all those speedups. So it is probably the case that good problems for quantum computers are those problems where you ask questions about some global properties of a certain object, certain pattern, certain functions. But this is just a work in progress. So there are many things you can say now about quantum algorithms. I only just really scratched the surface of the whole field that is growing. I'm not going to go into other directions that one can talk about another form of quantum computation, the so-called adiabatic quantum computation. One can explore the field of different algebraic structure that you think are good for quantum speedups, like the hidden subgroup problems and so on and so forth. So we are not going to cover this in this introductory course. Instead, we are now going to move into what may sound like a more practical question. Namely, can we implement all those wonderful things? Can we do something to make it happen, right? To make it a real physical computation in your lab. And that's tough because quantum computers are very fragile objects, in a sense that if you don't confine your computation to a piece of hardware that you want to control, it just spills out. It just interacts with the environment. It dissipates. All this quantum interference goes in the wrong direction. And can we do something about it? So that's our next topic.